Okay, we're looking again at areas under curves, and this is we're looking at 2b. Um, our first step is to try to write some expressions that will allow us to find the area of each of these individual rectangular intervals. So if we look at our step one is to see if we can figure out how to write an expression for the width of each of these rectangles. Well, what we're going to do here for the width, since area equals length times width, for the width, we're going to take b and subtract a, which will give us this distance. And then we're going to split that n ways. We don't know how many ways yet, so we're just going to leave it at n. And we want to find the height. What we need to do is we're going to find whatever our x value is, and our x value is going to be the right-hand side, or the height of this rectangle. And so we're going to find that x value. The way that we do that is we're going to do a plus whatever the width is, and that's going to get us to our x value. Why is this helpful? Well, because the y value is the function, so y equals f of x. So if we can find x, then we're going to plug x in here, and then it's going to pop out and tell us what y is. Well, we just found x. We said that x equals a plus b minus a over n. So we're going to take this and plug it into our function and see what pops out for y. Well, the interesting thing about this function is x equals y. So when we found x, this thing, we also found y, which is going to be our height. So our height is a plus b minus a over n. Now, we're going to need to figure out some way. Well, okay, well, let's keep moving. We'll get there in a second. So now we can take these and we can write an expression for the area by multiplying these two together, which is what you see here. The only difference here is what I've done is I've indexed this to account for the fact that the height of each rectangle is going to be different based on which rectangle it is. If it is the first rectangle, then k will be 1. And if it is the second rectangle, then this will be 2, because I will have my x value will be 2 times the width, which is this thing, plus whatever a was. And so then remember that I will take that and I will plug that in the function, and that will give me, so then this is my y value, or my height. Okay, so hopefully you guys can see what we did there. Now, to find the area of this stuff underneath the function, we need to take the area of each rectangle and we need to add them all up. So we already said this thing is the area of each rectangle. Now we're going to have a lot of those. In fact, however many rectangles is what we're going to have. So we could take all of these and we could add them up, but that's just going to take us a really, really, really long time. So let's take a look at this and see if there's something else that we can do. So you see what I did here is this first piece represents the area of the first rectangle. This piece represents the area of the second rectangle, and all I'm doing is I'm adding those up. If you notice, as I add those up infinitely, what happens is that all of these have some different things in common. You notice that they all have a b minus a over n in common, and they would continuing. So what I'm going to do is I'm actually going to take this b minus a over n and I'm going to factor it out. So I'm going to pull it out of all of these. And what happens is once that is gone, then I'm left with, or not gone, excuse me, once that's factored out, then I'm left with this thing, a plus 1 times b minus a over n plus a plus 2 times b minus a over n plus a plus 3. And that's going to keep going. Well, there's another pattern I want you to see. And at this point, all we're doing is we're just algebraically manipulating things. And my apologies, this should not be here. So ignore that, please, and ignore my messiness. Okay. So we've factored out the b minus a over n right here. So here's where we are. Pick up here. And what happens is, so this piece that's left represents the first rectangle, and here's the second one, and here's the third one. If we multiply those, if we're distributing again, then that would give us the area of each rectangle plus all the way up to this thing. Now, the other pattern that you notice is each of these, they have an a in common, so let's see if we can factor out an a. So instead of having to add each one, what happens then is we're going to do the number of a's that we have times a, or times the value of a, which is just going to be a n. We're also going to notice that we have another b minus a over n in common. Here it is. So let's factor that thing out. So when we take that out and we take the a out, what we're left with is just 1 plus 2 plus 3 plus 4 all the way up to n, however far n goes. Now, why is this helpful? It's helpful for several reasons. Again, all we're doing here is we're just manipulating. We're trying to get to a situation where we have something like 1 over n. Because as n approaches 0, or not 0, excuse me, as n approaches infinity, this whole thing, 1 over n, approaches 0. So let's see what we can do as our next step. So now we've factored everything. So actually now let's see if we can work back the other direction. We do b minus a over n times a over n. We have an n here that will cancel. And this leaves us with a times b minus a, which is this thing. Now, let's go ahead and distribute again. B minus a times b minus a is b minus a squared. N times n will give us n squared. And we still have this piece here to try and work with. Now, let's use something that we did earlier. So let's take this 2 and the n squared, and we're going to swap places. So this is no longer going to be n squared, it's going to be 2, which brings us here. This is no longer 2, this is n squared. So we got this. So all we're doing here for this next step is we're just going to split this n up. So one of these n's is coming over here underneath this one, and the other n is going to stay here, which brings us to this point, n over n times n plus 1 over n. This is helpful because n over n is just 1. We're making progress. Now, the next step we want to do is we want to take this n plus 1 over n, and we're going to split it again. Now, when we split it, we're going to end up with n plus n, this should be a plus sign, plus 1 over n. Now, this is helpful as well because, as we know, n over n is just 1 again. So we have 1 plus 1 over n. Now, at this point, you're going to have to follow along with me here and see what we can come up with. So now we have a simplified version of the sum of the areas of all of these rectangles. So all we did was this is the area of all of these rectangles, and we just manipulated around, and here's what we came up with. So now the cool thing is as n, so we'll write this thing out. Let's bring it up here actually. So the limit as n approaches infinity of the sum equals, well, remember, as n approaches infinity, this whole thing, 1 over n, approaches 0. Which means then that this is actually going to be 1 plus 0, which is just 1. So then we end up with 1. So this is all gone because it doesn't really matter. So then we end with 1 times 1, which is just 1. So those are all gone. And 1 times this thing is just this thing. So here is our solution for the area. So here we go. A times B minus A. What did we have left over here? Plus B minus A squared over 2. There it is. Now, we can probably go a little bit farther with it. So let's see if we can actually make this thing work. So let's take and distribute this, which will give us AB minus A squared plus B squared minus 2AB plus A squared over 2. Let's go ahead and get a common denominator here of 2, which will make this 2AB, and this will be negative 2A squared. So now we can go ahead and combine these things, and what happens here is we have a 2AB that's going to cancel out, and we have a negative 2A squared that will combine. So this thing right here will combine with this thing and give us, let's write that first, it's alphabetical, so negative A squared. Those are done and gone. This thing is still here, so that's plus B squared. Let's bring our denominator over, and that is all over 2. And there's our final answer.